ancient volcanic eruptions disrupted Earth's thermostat, creating a snowball planet. Grant Cox, University of Adelaide, on The Conversation reports, one of the most extreme climate episodes the Earth has experienced was during the so-called snowball Earth 720 million years ago, and during this period glaciers spanned from the poles to the tropics, resulting in a planet entirely covered by ice. The snowball Earth hypothesis has been the subject of scientific debate for around 20 years. Scientists are both fascinated and perplexed about how the planet could descend into such a weird climactic state. But new research now points to spectacular large volcanic eruptions as being key in this process, and we suggest this happened because large amounts of carbon dioxide were pulled out of the atmosphere after huge eruptions, and this led to a loss of heat from the Earth's surface. So that makes us realize that the tremendous amount of carbon dioxide that's put into the atmosphere, heating up our climate, is essentially some kind of a radiator, thermostat type of an aspect on the Earth, geology and weather. Now, surprisingly, the mechanism for this appears to be the rock erosion. Kindly support my Patreon account since YouTube has again demonetized my YouTube channel. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. Different kinds of volcanoes. Relationship between volcanic eruptions and climate are well established. For example, sulfur injected into the atmosphere from the 1991 eruption of the Philippines' Mount Pinatubo lowered global temperatures by about half a degree for 15 months. The sulfur reflected incoming solar radiation and lowered global temperatures. Now, volcanoes like Mount Pinatubo are part of volcanic arcs that produce relatively small volumes of eruptive material. Across the world, arc volcanoes together produce less than 1 cubic kilometer of eruptive material every year. Compare this to a type of volcanic eruption referred to as a large igneous province. We'll refer to them as LIPs. These eruptions are spectacularly large, producing in excess of 100 square kilometers every year of lavas, and crucially have total eruption volumes in excess of 1 million cubic kilometers, covering areas greater than 1 million cubic miles. For comparison, the area of South Australia is roughly 1 million cubic miles. Now these are, cubic kilometers. These are continental scale resurfacing events. More than 300 of these LIP eruptions have been recognized throughout Earth's history, and they appear to peak in semi-regular cycles. Long-term climactic effects. While some relatively small volcanic eruptions will have short-term climactic effects, the long-term effects of LIP volcanoes may be profound. The reason for this boils down to simple chemistry. Carbon dioxide in the atmosphere dissolves in rain and falls to the ground, where it reacts with silicate minerals in the rocks. Carbon dioxide forms bicarbonate and ultimately becomes locked away in limestones and shale rock formations. Over hundreds of thousands of years, the amount of carbon dioxide in the atmosphere is quite effectively regulated in this way. Scientists estimate that weathering of rocks consumes approximately 600 million tons of carbon dioxide every year. Geological formations for LIP volcanic eruptions are particularly susceptible to this process, as they are largely composed of basalts, which is a type of fine-grained volcanic rock that weathers relatively quickly and soaks up carbon dioxide more effectively than other rocks, such as granite. But LIP volcanic eruptions can also affect climate in other ways, through triggering photosynthesis. Linking volcanic eruptions to photosynthesis might seem strange, but it all comes down to nutrients. We have recently shown that the erosion of geological formations such as basalt from LIP volcanoes fertilizes rivers and oceans by releasing phosphorus. Phosphorus is an essential component of DNA, and all life requires it. Over long time periods, phosphorus is a nutrient that regulates the rate of photosynthesis. And when photosynthesis takes place, it too pulls carbon dioxide from the atmosphere. Descent into Snowball Earth. Our most recent paper focused on determining if the erosion of basalt from LIP volcanoes contributed to the reduction in atmospheric carbon dioxide associated with Snowball Earth. Initial modeling predicted a halving of atmospheric carbon dioxide would be required to drive the Earth into the snowball state. And to do this, we measured different forms known as isotopes of the rare earth element neodymium, Nd for short. That's the chemical symbol for it, Nd, that track the erosion of basalt in sedimentary rocks. We particularly focused on the contribution of eroded basalt in shales, which are rock formations created from continental erosion. Now, I never knew how shale was made. That's how it is. Rock formations from continental erosion. Also, we measured isotopes of the element strontium, Sr, in limestone, which record the chemical composition of ancient seawater. And from this work, we found that basaltic erosion just before the snowball Earth was more than 100% greater than we see today. This basalt was sourced from the three prominent LIPs, which erupted in a cascading sequence beginning 830 million years ago in Australia, 780 million years ago in North America, and 720 million years ago in northern Canada. All three of these LIPs erupted in what was then the equatorial region, which favors fast erosion due to warmer temperature and higher rainfall. Finally, the impact of sulfur aerosols released by northern Canada's Franklin Large Igneous Province just prior to glacial onset may have also induced further global cooling. It's likely that this unique confluence of events allowed the planet to tip into a frozen abyss. Complex interactions in the Earth system, atmospheric carbon dioxide levels and global climate are regulated over long periods of time by weathering of rocks. Over geologic time, hundreds of thousands of years, this process acts as a negative feedback on increasing atmospheric carbon dioxide. When higher temperatures drive higher rates of weathering, it acts as a kind of thermostat for the Earth. But this work demonstrates that the Earth's thermostat can fail spectacularly at times. The eruption of LIPs resulted in a snowball Earth. This period of time lasted from 720 to 635 million years ago and is known as the Cryogenian. It is a time of continental breakup and marks a major transition from a world dominated by bacteria to a world dominated by more complex life. This highlights the complexity of the Earth system and the unexpected interactions between volcanism, climate, and life. Amazing. This is by Grant Cox, University of Adelaide, on the conversation. Please leave your comments and thank you for your support.